Okay, so hello everyone. Thank you for coming. So today we'll continue with the questions regarding robustness of models. So how can we make models robust against especially adversarial examples? So we'll continue with the questions that were posted to forum. So last time actually we had, I would say, very complex questions. So we didn't go that far, but we can just continue where we stopped, and hopefully we can cover all the questions by the end of this lecture. Any questions from you guys before we get started? Okay, no questions. Okay, good. So last time actually we finished on the question that was regarding this, I would say, trade-off between the clean accuracy, so performing classification on just clean samples without any perturbations, versus the perturb adversarial examples. So what we discussed last time was that actually to achieve the both robustness and high accuracy at the same time, it's really impossible. Like as of now, in practice, we didn't see any model that would perform amazingly high on clean samples and at the same time be robust. So there's always a trade-off. We have to, usually in practice, we have to decrease a bit the clean accuracy to then get increase in the robustness to adversarial examples. So then is a question from Ahmad. Is Ahmad here? I think Ahmad is not here. And so Ahmed has actually questions regarding Simba. So it's kind of easy. So in the sense that yes, Simba starts in a random location. So depending where you start, then you might have different performance of the attack. And then so what we saw is that there are many different ways how to make models more robust. But one of them is actually that we train bigger models. So then this actually causes the problem that if we would like to deploy a very robust model on the devices, like a small, let's say, smartphones or other like hand-in devices, then actually this becomes a problem if we really want to ensure robustness. So in some cases, what's happening is that you submit some form of input to the model. However, the model is deployed remotely, and you just actually from your device, a given sample is sent to the server where the example can be handled by a big model. Okay, is Shreya here? Okay, hi Shreya. Thanks for coming. So Shreya asks in the lecture, the optimal labeled to unlabeled ratio per batch was explained as 3:7 because we should proportionally weight the unlabeled data. But what I didn't fully understand is why having too much labeled data, like at 9:1 ratio, actually performs worse than having very little labeled data at 1:9. Shouldn't more labeled data always help at least a little, since the labels give stronger supervision or signals? Okay, so thank you for the question. Maybe we can just see this ratio. So the result in the graph actually was empirical, right? So this one, right? So basically here we basically experimented with these different ratios, and then we found that for this ratio 3:7, actually we had the highest robustness, right? And so ultimately, how I see that is that training with supervision actually might be not the best approach. Why? For example, we have this example of cat and dog. So you have cats always at home and dogs always on a green grass, right? And then you have these training samples and you always have this background, and the model basically to classify better just leverages the background, right? Without learning what's in the images. So just model is purely biased to this totally irrelevant features. And then when you give to the model example of a cat on a green grass, naturally model says it's a dog, of course, right? So model picks up on any features in the images that can improve the classification. So in some cases, if you just do this supervised learning, then model actually is forced to learn features from the data and not just to have the shortcuts to classify correctly. So then if you do this even pre-training on just images purely, then you might get actually these stronger features, more robust features, and then only, for example, do fine-tuning with classification in mind, and actually then you might obtain a more robust model. And actually one of the approaches is really that popular now is that we do SSL, and the supervised learning at the beginning on a large scale of data and with big models. And then we only adjust to the at the very end, the model to classification task, also on the small number of samples. We also saw this aspect of semi-supervised learning. So you do have some part of samples being labeled and some of them being not labeled. And actually, also over there, we saw that we can train model with really high performance. Does it answer your question? Okay, thank you for asking. Um, right. Sorry? Yes. I just answered that. Okay. I just answered at the very beginning. Sorry? So you just came? Yeah. Okay. Okay. So, just okay, just for you, a small recap. Also for you, I suppose. So, okay. Yeah, I thought that we covered it a bit last time, but in principle, um, there's a trade-off. So you cannot really have at the same time high clean accuracy and high robustness. So if you want to get high robustness, you really have to trade a bit the clean accuracy. And in practice, we haven't seen any possibility of, as of now, having both robustness and clean accuracy at a very, very high level. Okay. And so there is question from Umar. Is Umar here? Oh, it's over there. Okay. So you have questions from the last row? Okay. So looking through the adversarial ML robustness slides on page 46, maybe let me go there. Was it this one? I think this one. It talks about how adversarial data completely consumes model capacity. Is the takeaway basically that we just have to use massive models like Resident 50 or VITs to get any decent robust accuracy? Or are there clever ways to train smaller models without them completely collapsing unperturbed data? Okay, so basically what this graph shows is that models can become more robust if you basically use bigger models, right? So model capacity actually is important. So with more capacity, we can have higher robustness. This is what this graph clearly shows. And of course, this is one of the ways how to make models more robust. We also saw under other different choices of like how to make models robust. So for example, here we showed basically that if you choose, in this case, this um, uh, wide ResNet with 46 as the number of layers is more robust than model with 28 layers, right? So you might also just choose different architecture, not only just how many parameters. Also, we talk about these different activation functions. So you might make your model more robust, not only by higher capacity, but also, for example, by, in this case, using swish or silu activation function. And there's also a question about that, actually. So robustness can be done with different approaches, can be achieved using different techniques, activation functions, architecture choices. So ultimately, you can get even small model to be more robust, not only by increasing its capacity. Does it answer the question, Umar? Okay. Right.
Because if we increase capacity, we increase the capacity. So just models are basically the 400% effect because of underfitting.
But so ultimately, model can pick up on this non-robust features, right? So it okay, so it might even not okay, it underfits, right? or can even overfit, right? And this is okay, so it can overfit to the non-robust features. So for example, this aspect of like picking up on the red, okay, basically green grass and some background at home. So can overfit to these features and then still be, of course, not robust, right? So I think that we should not narrow down like the whole problem with robustness to just one element. I think it's a more complex problem. Okay. Okay. Is Anika here? No. Okay. I find the question to be interesting. So actually, Anika was asking, so why should we choose adversarial training versus randomized smoothing? So randomized smoothing is a theoretical approach how to make models more robust. And actually, what is the problem is that the radius that is for which the network actually is robust is much smaller for certified robustness than for adversarial training. So in practice, if you really want to have a robust network, then I would highly recommend doing adversarial training and not only relying on certified robustness. That being said, there are ways how to combine both. So also Anika asked if we can have these two methods complementing each other, and actually it's possible that you at the same time do certified robustness and adversarial training. There are some requirements to really make it work together both, and one of them actually is that you have to also train this network to be robust with let's say random noise. So you have to make the network also smooth, and then this also facilitates doing certified robustness. So I also posted a paper in forum for this thread, where you can basically check that how in detail it can be done. So okay, Anika is not here, so unfortunately we cannot continue on that. Just to cover all questions that actually also you have. Okay. Is Ridvan here? Okay, Ridvan is over there. Thank you for coming. So, Ridvan asks about the black box transfer attack. How similar does a surrogate model need to be to the target model for adversarial examples to transfer reliably? Does architecture matter more than training data? Okay, that's a very good question. So, overall, this aspect of transferability is, I think, something that surprised to some extent researchers, because you can transfer between, let's say, ResNet and VGG, or ResNet and transformer architecture. So this was something that was a bit unexpected. That same um, same objective of training, but different architectures totally, and you still can transfer and sell examples. So that's also why it helps to steal the model first before applying these adversarial examples to fool the model. So now, what really helps the most? So ultimately, what is the most important aspect is actually data. So here we have different architectures, different activations, different number of layers, and this example is transfer, right? However, mostly they are trained on the same training data set. So for example, you train on CIFAR10, right? So why this the case? So I would say I would go back to our previous lecture where we discussed dataset inference method. And we talk about that training samples influence decision boundaries, right? So the training samples decide decision boundaries. And if you train with the same data, then ultimately you have similar decision boundaries between two models. And this is why this actually examples can transfer between these different models. However, if you train let's say two same networks, let's say ResNet 50 on ImageNet and CIFAR10, you attack one of them with for example, you have also different classes, right? Then the example does not transfer. that well, right? So with different data, it basically doesn't transfer. In principle, you can find that you train on entirely different data sets, right? You have different classes, of course, it doesn't transfer, right? So the most important still aspect, I think, is the data. Does it address your question? Okay. I think so. Yes, I think that otherwise you won't have this transferability. Yeah. So yeah, I did some experiments with Svarten long ago, and yeah, it was for me even surprising how well it transfers. But ultimately, we just tested transferability between networks and not just different data sets. Yes, because ultimately, what you want is to attack a given model, to fool the model that should be a class, let's say dog, but model predicts cat, right? And if you have different classes, then there is no really like a way how to really do this transfer, right? So ultimately, data counts the most. Okay. And is Lavanya here? Okay, I think Lavanya is not here. Lavanya had a really, I would say, extremely long questions. Yes. So what actually Lavanya asked was the differences between convnets and vision transformers in terms of robustness. And she also mentioned that in convnets you have kind of built-in invariant property of the convnets to, for example, rotations. So the plain vanilla convnets actually, I would say that are not that invariant to even rotations. So we had actually this example with um, building watermark on the rotation. So we additionally actually trained network to be able to recognize the rotation angle of the given image. So even in our case, actually we use rotation specifically to build in watermark into the SSL models, if you remember from the steering part. Now, even in the case of transformers, actually, they are trained with augmentations. So let me just go back to this. Hmm, um, so I think that. Oh, okay. So we talk about this aspect of the transformers. Ah, yes, it's here actually. Okay, so also Lavanya talk about this aspect that CNNs can focus on one patch of the image. However, it's also the same for transformers. So they actually also patchify the image, and actually these patches of the image, also with the attached positioning, are run for the transformer. So you also have actually patches for the transformers. And there was this aspect of like global attention, if this would make the models more robust or not. So actually, global attention might be also a problem because you basically can look into specific aspect of the image, and then this basically aspect would dictate what is the global feature of the whole image, right? So in some cases, global attention actually might make this model less robust. And what's more is that so regarding rotation, other aspects, we also train transformers with augmentations. So usually when we train any network, we do apply different augmentations of the images. And for example, SSL applies very, I would say, strong augmentations, like the angle of rotation is pretty large. So these also networks, also by the way we train them, also become to some extent invariant to augmentations like rotation. So I would say it's not like inherent thing that makes one model architecture more robust than the other. It's really about ultimately how we train these models. And then the aspect that is important for the transformers is that we can really make them huge and still be able to train them. So convnets cannot really scale to the number of parameters that we do now train these models with. So for example, you know, models from Anthropic or OpenAI have number of parameters like 700 billion, not reported fully. But so you have really immense scale of these models, and training such convnet specifically is not possible. So this aspect of transformers really is about we can you know, ultimately, if we would have enough compute and enough data, we would just train these models on all possible augmentations, all adversarial examples, and then, you know, they would be more robust, right? So if you would do brute force, then you would actually do that with transformers and not with convnets. And also there was question regarding how we can make SSL models more robust. So I think that we discussed actually that last time, I think. So yes, actually it was this part. And here actually the idea was that we do two-stage training. So we do train first SSL model, and afterwards we make this SSL model more robust. So here really, why do we do that? It's only because of the um, performance. So if we would do that at the same time, so we would do SSL training and adversarial training, then actually our training would be of complexity n times n, where n is number of augmentations and n is number of iterations for PGD attack in this case. So by decoupling these two stages, for especially SSL, which are also big models, then we have this complexity O of n plus n, which is of course um, much better. Yes. So if so, I think that the question was, if let's say that in the first stage the network becomes not robust, can we make it more robust in the second stage? Yes. So actually, the second stage is really to make this network more robust. So this actually is the main part where we can afterwards, kind of post hoc, make the network more robust. Okay. Okay, is Osama here? Okay, thanks for coming, Osama. Yeah, so just I think last time we didn't finish all the questions. We had also tutorial, we had also presentations from you guys. So we had to just stop. But I think that the point of this part of the lecture is to really also have with you discussion and really, you know, discuss and explain these most difficult parts so that you can you know, just understand that and not focusing on everything, right? Okay, so question from Osama actually is regarding pre-adversarial training. So we can also just go to this part of the lecture. Okay, so this was actually the description, what's happening, and also there's algorithm actually from the paper that shows how we do this free adversarial training. So the lecture highlights that the free approach is 7 times faster because it uses a single backward pass to simultaneously compute gradients for both the model parameters and the input perturbations. However, in standard PGD training, the input perturbation is optimized while keeping the model weights fixed at the step, whereas here both are updated at the same time. Does this simultaneous optimization create a moving target problem where the generated adversarial noise becomes slightly misaligned with updated decision boundary? So, so actually, I think that the biggest problem is that finding adversarial examples with 7 steps of PGD is creating a much stronger example than with 1 step or 2 steps or 3 steps until reaching the 7 steps. So by training the model with this more challenging example, actually, I think that you can make model more robust. So this is how I would interpret actually this training. like free versus standard adversarial training. Also in the lecture, also we mentioned that this replay, so you actually do the training with replaying the same mini batch, in this case 7 times, if it's a PGD 7-step, right? So actually this lowers the statistical efficiency of the training process. So in the training, it's much better if you, for every single iteration, use different mini batch. So also actually this aspect, I think, is what also makes this network, I think, not as performant as for standard training. And this was question. So if so, could this gradient mismatch explain the 4% drop in robust accuracy compared to standard Mondrus training? Or is the drop mainly caused by the localized nature of the warm start perturbations? Yes. Yeah, so I think that's, for me, I think that this is one of the aspects. So we replay the same mini batch many times. Plus, we don't train on the hardest possible example, which was find after 7 steps of PGD and with this like intermediate steps of PGD. And yeah, I think that also we show that the difference, right? So indeed, like the training time for free with m equals 4 is like yeah, almost 6 times faster. But also then you have drop in robustness for PGD. Like for PGD 20, the drop is like 4%. So I think that's 7 or 6 times faster. Okay, so basically, I think that there is no like free lunch. So you have to choose your battle. Either you know train longer and you have more robust model, or you just save on compute like 7 times faster. Okay, and then you have a bit lower robust accuracy. So I think that it's also a trade-off, right? So M actually is how many times we do the we do reuse the mini batch. So basically, here in the line 4 of the algorithm, you choose a mini batch from the samples in X, and then actually m iterations, you reuse the same batch. Sorry? I didn't hear. Which here? Okay.
We reuse template along particular or reuse once and then replace it sometimes.
So basically, here what it says is that so you choose a mini batch, right? Then you keep the same mini batch for this m iterations, right? Then you update model parameters theta with stochastic gradient descent, right? So this is basically standard gradient descent. So you compute the gradient, and basically then you update the model parameters theta with this gradient. And then use gradients calculated for the minimization step to update theta. So actually, here is adversarial example part. It's actually PGD step, where you basically take the sign of the gradient, multiply by epsilon, so your strength of the attack, and then you basically add this to the perturbation delta, and so you clip the delta to be within this epsilon ball. So at the same time, for the given step, you update parameters of the model. So actually first you compute the gradient, you update model parameters, and at the same time you improve your adversarial example. Okay. Any more questions regarding this part?
What's the name Smoker? I didn't. Maybe I heard you. Also, like my name is Smoker. Like.
Sorry, Osama. Osama. Yes. Okay. Okay. Okay.
I think there is another person. Same name.
Okay. Okay. But you are Osama.
Yeah.
Who asked this question? Okay. Okay. Good. Does it answer your question? Okay. Okay, so is Atip here? Okay, thanks for coming. So the lecture said Swish Silu outperforms other smooth activations like Soft Plus for robustness. Is there a reason why? Okay, I think that's an interesting question. So yeah, what we showed in the lecture. So here we have on the y-axis robustness accuracy, and on the x-axis clean test accuracy. So ultimately, what we want is to have at the same time both test, clean one and robust one, to be high. So here, standard ReLU. So if I take any network, like by default, it has ReLU activation functions. For the clean accuracy, it's shown one of the best. However, if you want to achieve robustness, then actually it's better to, for example, use leaky ReLU. And this gives you actually at the same time both a bit higher clean accuracy and robust accuracy. However, if you want to even achieve higher performance, you might also use this swish or Silu activation function. And the question was, why using this swish or Silu actually performs better than using Soft Plus, right? And so first, I think that I wanted to just elaborate on these different activation functions that we have, right? So ReLU is easy. I think probably most of you, okay, if you took machine learning, if you had taken machine learning course, you had to learn ReLU. This is obligatory. So it is very easy. You basically have 0 if you are less than equal 0, and then otherwise it's just x, right? And also the Silu is kind of like a smooth version of ReLU, but can also go to this negative value. So basically Silu is x times sigma of x, and basically sigma is just sigmoid. So it has this kind of here a dip, and this actually makes this Silu possible to also transfer some negative features. And then also there is Swish. So Swish actually is a version of Silu, which adds this parameter beta. So basically this parameter beta can control, you know, how deep is this dip, right? And also we have standard sigmoid activation function. So I think, okay, you should know it. Also there is this ELU. So then it's simply same as ReLU. So basically it's x if it is greater than or equal 0. And then it's other function. So alpha times e to the power of x exponent of x minus 1 if it's less than 0. So actually this gives you kind of this smooth function, which basically is here visualized. And also we have Soft Plus. So how you can see Soft Plus is that it's really almost like ReLU, but it basically is smooth. It also never goes below 0, and basically gives you this smoothness. And I think that the question is really like, so why in this case Swish or Silu outperform Soft Plus? So in general, both of this, Swish, Silu, and Soft Plus, they really make ReLU smooth, right? So actually, this part is the same. Now, what actually is different, and what? Okay, so this is kind of speculation, right? Like, why this Silu or Swish might be better, apart from just seeing experimental results, is that actually they also have this aspect of you know, mostly being Silu is mostly like ReLU, right? I would say in most cases I see Silu, so you can optimize better, right? To be as close as possible to ReLU, but also have this negative aspect. And this might, for example, enable you to, in some cases, have this like negative features, right? So this is something that that, for example, Soft Plus cannot do, but it helps still in this, especially this this part of which actually is non-linear for ReLU, really make it smooth, but also get some small aspect of negative inputs. Yeah. So it might help the network to just learn some negative features and maybe like balance more internal representations. So this is one of the ways how I would interpret it. Yeah. So kind of like what is important also that soft plus is mostly positive. So it can also might also just induce like positive bias in the network. And so if you see like a soft plus, it basically is almost most of the time is positive. And then it's basically value is also it goes to basically 0 if it blocks a given activations. So it is kind of for me interesting that with this dip for the silo, you might actually represent some maybe more complex decision boundaries. So this I think is kind of like a speculation why, which experimentally it is, right? And quite substantially. We can look into the function, how it behaves, and then infer this potential reasons why. Yes. But probably it'd be good to have some experiments, and you could run to, let's say, control beta in Swish, and then check, for example, like if we have a smaller dip or larger dip when the network is more robust. So I suppose that the best way would be to just have a battery of experiments, or then basically analyze, maybe narrow down exactly which part of this Swish actually make it more robust. Does it answer your question? Okay. Yeah. Also, there is, I think, the same question as the previous one regarding the transferability of the attack. So transfer attacks seem to work because different models latch onto the same non-robust features. So could an ensemble of models deliberately trained to rely on different non-robust features be used as a defense against transfer-based attacks? Okay, I think this is a great question, to be honest. So at the end of the lecture, we talk about open problems. So it's still not clear how to make really networks more robust. Okay, we have ways, but there is no like definitive answer, and it's still something that surprises many researchers. It's active area of research how to really make networks more robust. And I would say this aspect of the ensemble kind of falls into this part of the iterate of this enumeration. How can we create more robust models? And I would say that having the ensemble usually helps even for standard performance. So even if you just train one network, you measure clean accuracy, versus if you train many models and you just combine their outputs, it's usually slightly better. It's like 2% difference for, let's say, clean accuracy. And same thing happens for robust accuracy. It can get a bit more robust. However, definitely it's not like a solution. It is something that just can make the network more robust. And from the perspective of attacker, it's more difficult to attack the ensemble, right? So if you have one model, you can just use standard PGD attack, you can just compute the gradient, and you are done. For ensemble, it's a bit more difficult. You really have to take into account different networks, and then it becomes a bit more complex. However, you can still compute these examples as adversarial, even if you have like this large ensemble of models. Okay, but it's a really excellent questions. Thank you. Do you have any follow-up? Okay, thank you, Atip. Okay, and there is a question from Mahmoud. Okay, thanks for coming, Mahmoud. So Mahmoud asks, if a model is adversarially trained against one attack, for example, PGD, how well does that robustness transfer to different attacks, not included in training, such as black box Simba queries? Is it an endless cat and mouse cycle where every new attack forces us to retrain? So this actually relates to one of the parts of the lecture. So we talk about this robustness against multiple, in this case, norm attacks, right? But the same holds for different types of the attack. So you can have actually also here is so the blue line actually is for PGD style, right? Because you have L-infinity norm, and L2, for example, is Kalini-Wagner because it's L2 norm, right? So what is the bottom line is that even if you train for robustness against PGD, so like the blue line, also you increase slightly the robustness against other attacks. So making model robust in general makes it robust, to more than just a single attack. However, if you really want to be robust to all of these different attacks and different augmentations, then you should actually train on all of them. And yes, I think this is the issue that if we really want to be fully robust, then we should really train on all possible augmentations, all possible attacks, and then this higher model capacity, so let's say transformers with billions of parameters, actually would help, right? Okay. And then another question is, could adversarial training make transfer attacks more dangerous by focusing the perturbation budget on the very features that define the class, other than on unnecessary features that might not transfer? If so, does the parallel training become a double-edged sword, where protecting its own model while potentially arming attackers with a better surrogate for attacking unprotected models? Okay, so yeah. So in general, I think that okay. So why do you think, Mahmoud, that training adversarial training might make the transferability of the examples more dangerous?
So my theory or my imagination is what adversarial training do is makes a model focus more on robust feature rather than on unrobust feature. So if you adversarial train your model, you are not focused on robust, then use adversarial training as a surrogate, which will also focus on the state base, robust feature. So now I somehow managed to make the surrogate more aligned with the target in terms of pixel features that you need to focus on. So now my attack even gets much stronger.
Okay, but also the first model is trained to be more robust against the attack, right? So basically, I think the question is, do you make the model stronger in general, or you just make the higher possibility of the attack to be stronger, like the transferability to be stronger, right? So so once you find an example, does it transfer better to the target model than if we compare with found and example for the standard network? Yeah. So my hunch, so I haven't checked that. I haven't run experiment for that, but my hunch would be that transferability probably would work worse if you do adversarial training. Ultimately, the model becomes okay. No, I'm not sure, but it would be kind of something that we could check, right? So if you could run an experiment that you train models adversarially versus clean model, but then you have to really focus only on the success of the transfer of the attack, right? So once you find the attack on the surrogate model, then basically you check how this transfer to the target, right? Yeah. I suppose there is some research about like transferability between the robustly trained models. So probably we can basically check if there's any paper regarding that. Okay. So next question is from Isam. Is Isam here? Okay. Thanks for coming, Isam. So Isam asks for transfer-based black box attacks, what makes adversarial examples transfer between models? So in both cases, if it's a white box or or black box, basically that. So what makes it possible to transfer the examples is the construction of the decision boundaries. So if the models are trained on the same data, they usually create similar decision boundaries and then enables us to transfer the attack in both. Like, so you can also do it in the white box, right? Um,
Like definition of black box, right? But if we don't know the data, we can't guarantee that the decision boundaries are going to be similar for our surrogate model, right?
yeah, I mean that we cannot guarantee, but in practice we see that these examples transfer to target models, right?
Usually the black box case with the white box as well.
I mean that's so so okay. So you are talking about okay, sorry. I have it. I have it, I think. Okay, I talk about it here, right? Yeah. Okay. So I talk about this black box versus white box, right? But okay. So basically, if you have white box access to the target model, don't need any transfer, right?
So black box was just white box, but first we steal the model somehow, and then we do the same thing with everything.
Yes. So basically, stealing is usually done as the first stage before attacking the model like that. I mean, one of the ways how to attack the model, right? I mean, that nice part is that because creating strong adversarial examples might take you like 100 steps on the target model, right? If you want to do like bulk attack, then better if you steal the model and then you just attack the model, right? So basically, yeah, it's better. Okay, depending on the probability of the attack. If you have just, if you want to just attack one sample, one single image, like Simba, for example, right? So then, you might just poke the API with this small changes of the pixels. You just do 5,000 queries and you are done, right? But if you have a bit more like a larger set of samples to attack, and probably would make sense first to steal model or some kind of equivalence of the model, maybe just enough to craft answer examples.
Is there any work done where you can't steal them? Like for example, like GPT-5, you can't have anything similar to that.
So basically, there's a paper that showed how to steal exactly the last layer from GPT models from the API. So basically, they steal exactly the parameters of the GPT model. Like I think it was GPT-4. So basically, yeah, especially for these big companies, actually stealing is apparently nowadays a big issue because you basically there are many court cases where okay, so big aspects like DeepSeek apparently stealing from OpenAI, right? Or Grok stealing from OpenAI. So stealing is also a way how to stay cutting edge to your basically competition, and it was shown that you can really steal the even parameters of these models And well, this can be a first like kind of reconnaissance attack before you just attack the model with some maybe adversaries.
I'm not very sure about the attempts and connection and but for image and computer vision shouldn't those models, any type of application that you are using, see the same features, the same data. For example, for the photos that are in front of me right now, even if you have a model and using a surrogate model, both of them should see the same feature. It's going to be the body, the mouse, whatever it is. So why we need to use or to see a model for a translation, just a surrogate model, any different surrogate model should work.
So you steal the model in this case to copy the certain boundaries, right? So by getting the outputs from the target model, you can just better model this model behind the API on your own local copy.
But if I code some of them, so while I'm more focused on attacking it, anyway, I already have some of them.
Can you repeat? What's the question? Yeah. Easy. So for example, let's say I have a car, Tesla, and I drive Tesla in a certain location. Tesla has basically model to recognize street signs, right? You steal the model from Tesla car, and then you basically make sure that this stop sign that is on my street actually becomes speed limit 100. And next time I just drive 100 on the stop sign. Hopefully you won't do that. Okay, many questions. Okay, maybe you have, okay, go ahead.
If you look at the back safety, the definition we do, and the operation we do to trick the model, right? There must be a degree where, like here we trivial if we can just swap the image from a dog to an actual cat, and make the model produce a different prediction. Right? There must be, but by that point it's trivial. So how do we quantify the amount of alteration we apply?
You just basically do the epsilon ball limit, right? So basically you check. So there are many ways how to check how much your modified image is different from the original image, right? So simple bounds on the distance, for example, between the target image and the perturbed image. Mm-hmm.
But we are basing it on the decision boundaries for the black box case, whereas in white box we use gradients. So can target be the same for white box case, where eventually by copying the gradients, the endpoint would be to still kind of mimic the decision boundaries in the end.
Okay, sorry, I think that's. Can you speak a bit louder?
Black box target to copy the decision boundaries. But
Yeah.
we talk about the white box where we kind of we have the gradients.
Right.
But the end goal would still be to kind of mimic the decision boundaries now by using the gradients that are available. So the end goal is always the same, which is to kind of mimic the decision boundaries, whether it be black box or white box.
But for white box, okay, so if I have white box model access, why would I transfer any example?
Thinking in terms of decision boundaries, because eventually, even if we have the gradients, we would, like we had Jacobian-based attacks, so in that case,
No.
we would still drive the gradients towards its boundaries.
But so okay, so if I have to attack a model that I have white box access to, and I just directly attack with the gradients, right? Why would I do anything else?
And what would be the measure to compare against? We'll be using the decision boundaries even in the case of white box, or we don't make use of decision boundaries at all.
In what sense for white box?
terms of the stolen models are being
Ah.
similar to
Ah,
victim models.
so you are in the selling part. So okay, so what's your scenario? So I steal the model, right? I mount the attack on the stolen model, and I transfer the attacked image to the target model, right?
We have the gradients is what I'm assuming. So it's not a black box attack, it's more like a white box attack. Somehow I'm still thinking transfer to white box as well, that because we have a surrogate model.
Yeah.
We somehow need to make sure that
Ah.
decision boundaries are set.
Ah. Okay. I see. So you're asking, okay. Yes, so for the attack to work well, once you steal the model, the boundaries that are between the classes should be this roughly similar, right? Okay, so we're kind of asking, so if I have to attack the model, should I use black box approach like Simba, or should I use like stealing the model? And it really depends, right? Like if I have to just do it, once a single attack, probably I would go for Simba, right? If I have to basically produce this answer examples for thousands of images, probably I would first steal the model, then mount the attack locally, and then basically send all of this in bulk to the target model. Okay. So there's also other question from Isam. If adversarial examples arise partly because models rely on non-robust features, can we identify and remove these features? Okay. Well, I think that's well, yes. I mean that you could do that, right? So how? No, I can imagine. So if I have the simple task of classification of the cat versus dogs, right? There are models that do detection of objects. To still identify in the training samples where the dog is or cat, just maybe cut off only this cat or dog, and then I would train on only these samples, right? So then I wouldn't be biased to like green grass behind the dog or like a comfy sofa behind the cat, right? So this would be probably one way how I could just focus on ears and tail. So pointy ears for cats and other kind of ears for dogs. So this would be like maybe one way how I would approach it. But of course, this makes you kind of data engineer. So you have to basically then engineer your data, which is very costly, right?
So you're basically just solving the problem overfitting in this case. This is exactly how which you
Yeah, I would say in this case, in my simple example, yes. I would not overfit to the background, right? Because there's no background. I would only focus on the dog. But it's not trivial. Why? Because let's say you have some skewed data set. So all the dogs basically are wearing jackets, and then model still picks up on this jacket, right? So you don't know what kind of features models pick up because you don't see them, right? So I think that you can probably always find some non-robust features. For example, maybe also just artifacts from the camera. So I take the photos with this camera and it has some artifacts, right? And if I take the photos, let's say outside, maybe I have more sun. So then my dogs are a bit brighter. And then if I put the cat outside, it still says it's dog because it has just a whiter skin or whiter fur, right? So I think that's just non-trivial to remove these non-robust features.
It's the same problem with overfitting.
Yes.
Perhaps
Yes.
the methods used to solve overfitting could be implemented here.
Yeah, I mean that's
yeah. I was thinking like there's lots of paradox.
Yes. Yeah. 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 I would say probably training with also training objective is important, right? Because if I do training just on the samples without labels, then I'm not focusing on specific features that help me to predict the class, right? So if I do SSL training, right? So I only extract features from the data, then I would never like pick up on this grass so much, right? If it gives me the better performance for the classifier, right? I mean, the classifier picks up on the grass, but SSL wouldn't pick that much on the grass, but would pick up more on like what are all the features in the image, right? So yeah, yeah, but definitely I can see that if you overfit less, and actually also you might be more robust, which kind of is a amazing example because then look, so so let's say if I have this Q data set, but I have train and test, and actually my clean accuracy is higher because I picked up on this non-robust features that actually help me to classify better these cats and dogs, right? If I do the early stopping, so I stop the training before I overfeed, then I lose a bit on the clean accuracy, but I might gain in this case, as you said, on the robust accuracy, right? This directly supports why we have this trade-off, right?
Same thing for like regularization.
Right, right. Okay, perfect.
Is it related to how Simba attack is created? Like, based on my understanding, Simba looks for vulnerable pixels, like to protect that, and that this non-robust feature is actually related to that.
I mean, okay. So basically,
I think in Simba we look for non-robust features
mm,
that are perturbed by the.
actually, I can imagine that. I can imagine that I have 2 pixel image, right? And I have very, I would say, simple thing, like classify my image with 2 pixels to one of the classes, 1 or 0, right? And I basically have 1 pixel being black or white, right? For this class, and I just change this pixel. So actually, it's robust features that I change, and this kind of like, let's say, fools this model, right? So I would say I wouldn't connect that tightly, because I could attack with Simba just robust features or like robust part of the image. Yeah. Okay, there is a question from Ben. Hi Ben, thanks for coming. So Ben has a question regarding free adversarial training. To my understanding, in standard adversarial training, the inner maximization finds the strongest adversarial perturbation for the current model first, before the outer minimization updates the parameters to improve the loss on this worst example. That's right. However, free adversarial training updates perturbations and model parameters simultaneously and reuses gradients across mini batches. Since the adversarial examples are therefore only partially optimized and may already become outdated after each parameter update, does free adversarial training still accurately approximate the original robust optimization objective? Is it clear how much robustness this approach sacrifices for its better computational efficiency? Okay, so I think that we are kind of back to the algorithm here, right? So, well, I think that you do sacrifice the performance, as we saw in the results, right? So we just talked about that, right, today, that we sacrifice the performance for the much faster training, right? And I think that, so for me, it's really the case that in this case, I don't wait until I have the strongest possible delta, so the strongest perturbation to train the model against, but I basically use already like even one step of PGD to attack the model. So I think that's it's kind of like, let's not wait until the very end, let's just attack now, and it still works, right? So basically, but you have some trade-off, right? So I think that this field training approximates the original robust optimization objective worse, because you don't really go to the strongest possible attack, but it's still an attack. So you basically you make the model more robust, even if you just have the slight perturbation. So this refers to this adversarial training, so equation 3. So ultimately, yes, the algorithm says kind of like maximize this loss, and then if I have only single step of PhD, the delta might be not optimal, so my loss might not be maximized for this given sample. It's untargeted, for example, right? And so you don't have the best possible delta, and then you don't minimize parameters of the model for this worst case scenario. Yes, and I feel it's also like one of the drawbacks of this free adversarial training, but of course it's free, so then you gain on the performance. Yeah. Yes. Yes. Yes.
Out there and for tournaments there, but I was wondering that whether like for large production models you can kind of whether you can estimate this loss and advantage before having to train your huge model robustly and then checking what is good. Of course, save you a lot of time.
Yeah. Yeah. So I think that there is no like any, I think, direct mapping that is always true from M to your performance of the model. Like even when I start training any model, I don't know where I will end up, right? There is always some stochasticity of training of the model. So if you add to this complex optimization also parameter M, it becomes even more complex, right? So I think that you cannot really predict from the get-go when you start training what kind of performance you would get. So this is really very, very hard question to answer. But you know, if I now would train even like so this was for Resnet 3210, but if I would now train some transformer, then probably I would say, you know what, I would like to train super fast, so maybe I'll take M10, right? And you know, so maybe this is kind of like good enough. It gives you kind of directions, like where I would like to end up in terms of robustness and how long I would like to trade. Okay. So there is removed question. Wow. Okay. And then question from, I think that this is question from Anushka. Is Anushka here? Okay. Okay. So Anushka has a doubt about adversarial training. During training, adversarial examples are generated using the model's current weights. But since the model keeps updating, those adversarial examples are no longer the strongest attacks for the updated model. So are we always training against a slightly outdated model? Sorry, attacker. Yes. I think that's, yeah, so basically, well, this is kind of best effort, right? You cannot do better. You just, for the current model, you just find the sole example, and this is the best what you can do. So yeah, it's slightly outdated, could be better, but you cannot do better than that. Yeah. Okay, and also I posted this paper that shows how we can find a synergy between randomized smoothing and adversarial training. So it's also the last post, I think, from me. Yeah. Okay. Any more questions? Okay, no. So are we gonna have a tutorial? Okay, so let's move on to tutorial. So thank you, everyone.